Cells are the building blocks of living organisms. Understanding its life cycle is crucial for medical and biological research that can result in innovative techniques in tissue engineering and cancer treatment. Even though a significant amount of research has focused on studying cells, it is still hard to pinpoint the mechanisms that allow for cell growth, regeneration, and metastasis. In a computer, we can add each mechanism at a time and evaluate its role in overall dynamics. In vitro, one typically grows cells on a stiff plane substrate. However, nature is not that simple. When using a bed of spheres, cell growth is affected by the sphere radius, where large spheres favor cell growth while small spheres hinder it. Cell adhesion is governed by the clutch mechanism that explains the cyclic stretch of a cell. We develop a model where spheres connected with springs contract to test the substrate stiffness. During contraction, if a sphere gets locked, a clutch is activated and the cell adheres. Otherwise, it detaches from the substrate. After some cycles, we evaluate the volume of the cell. We found that the clutch timings affect cell survival, and we observe a transition between survival and death. In a tissue, cells behave differently, especially as a response to external stimuli. When a cut occurs in the skin, the reaction starts with the wound closure. Experimentally, the wound appears to close exponentially fast. In the computer, we mimic this behavior by adapting the previous models where now the cells are organized in an hexagonal pattern and the springs represent the cell and cytoskeleton junctions. When we remove a cell, a new interaction is added due to the actin-myosin cable. By adjusting the parameters of the spring and the cable, we can obtain a closure time comparable to the experimental measurements, showing that the cable is the relevant process for wound closure. Cancer cells organize in spheroids, and occasionally some leave the spheroids, leading to metastasis. In the computer, we model the cells in spheroids as spheres connected with springs. At random times, cell protrusion attempts to leave the spheroid. This succeeds if the spring forces are overcome during the lifetime of the protrusion. As the spheroid evolves, we evaluate the invasion potential of tumor cells, while modulating different biological parameters that have influence in the spheroid dynamics. With this, we reach the end of our journey, where we show that, using simple interactions such as viscoelastic springs, we can simulate several mechanisms of a cell's life.